Alright, my name is Matthew Finlay, and this is my Lab 6 on magnetic molasses. To begin, the goal of this lab is to dig into Faraday's law by watching how a magnet falls to a conductive tube. As it drops, the changing magnetic flux creates an induced field, and you'll measure and analyze that behavior. Some of our materials were a smartphone, a bar magnet, aluminum foil roll, a meter stick, and then a cardboard tube. Our system was the falling bar magnet, and then our surroundings was the aluminum foil tube, and then the environment surrounding it, i.e., air, gravity, and everything outside the magnet. Some important principles included Biot-Savart law, which is a current creates a magnetic field around it, and then the field strength depends on how far you are from the current. Next is Faraday's law, which is a changing magnetic field through a loop creates an induced voltage, and then that induced voltage acts in a way that opposes the change in flux. Then lastly was Newton's second law, which is the net force on an object equals the rate of change of its momentum, and then Newton's third law, which is every force has an equal and opposite reaction force. Alright, for the actual experiment, we dropped a bar magnet through an aluminum foil tube and then recorded how long it took to fall. Then we did this 5 times and found the average time. And some assumptions that we made were that air resistance is small enough to ignore, that the magnet behaves like a magnetic dipole, and then that the only forces on the magnet are gravity and then the magnetic force induced by the currents. And then here's the actual data from our experiments. This just came to an average time of 1.24. Here's a more in-depth look at the data. See the average time at the bottom, and above is the actual values that we found that we inputted into our code, which will be on the next slide. And then here's the actual code itself. On the left is some of the initial conditions, as well as the actual creation of the aluminum tube and things like that. And then on the right here is how we actually ran the experiment, what was actually calculated. Uh, the force from the magnet, the force from the induced currents actually going in the positive y direction, and then gravity going in the negative direction. And then on the next slide, you can actually see what what the results of our actual code were. So here's our experiment to the right here. So as you can see, it sort of starts out going down fast. That's where gravity is stronger than the force from the induced current acting upwards. And as it sort of gets to the right here, it flatlines, and so that's where you can see like the two forces actually start to equal each other. So our dipole moment from lab 3 was very different from what it should have been. So that's sort of the reason for why it takes so long to flatline. And in an actual real world scenario, these forces equal each other a lot faster, and you get that flat line for a majority of the tube, not just at the end here. But this was our results for our experiment. So here's the actual interpretation of the results. So from Lenz's law, red shows a counterclockwise current, and then blue shows a clockwise current. So what happens if you were to flip the magnet? So it would still fall, but the induced current directions would reverse. And then how does this real fall time compare to the simulation? So the simulation is faster, likely because our dipole moment was messed up, but also because it ignores air resistance and friction. Then how does what does the velocity plot say about the forces on the magnet? So gravity dominates at the bottom of the tube, and then inside the tube, the magnetic forces grows and then balances out gravity, which slows the magnet and then flattens the curve. All right, next getting to our sources of error. One could have been measurement, so the timing of the start and stop wasn't exact, and then another one could be friction, the magnet rubbing against the sides of the tube. And then lastly, we had a bad lab 3 dipole moment calculation. All right, getting to the discussion. If the tube's resistivity were pushed close to zero, the resistance would drop a lot. With almost no resistance, the induced currents would become much larger. Bigger currents create a stronger opposing magnetic field, so the magnet would slow down even more as it falls. Cutting holes or slots in the tube would break up the closed loops where currents form. With fewer complete loops, the induced currents would be much weaker, so the opposing magnetic field would drop. That means the magnet would fall faster.